Good morning. This morning I want to welcome you to Algebra 2, Lesson 1, Real Numbers. In this lesson, we will begin discussing, just trying to make sure that I'm still on camera, we will begin discussing a little doorway here. You notice the door is closed. We are going to be looking at closed number sets. In closed number sets, it always has to be considered under an operation. Okay? So, for example, let me just give you a set and explain what I'm saying. First of all, the set has to be defined. So let me give you just a set of 0, 1. Now on 0, 1, notice the little set symbols there. That indicates that that's the set. And in order to look at whether or not it's closed or not, we have to have an operation. Okay, get our big operating lamp out here. And it's shining down on this operation. The operation will be, let's look at multiplication for our first one. Okay, so we look at multiplication and we say, is this set closed under multiplication? Well, we think of all the examples we can within the set. We have to use numbers within the set. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. And 0 times 0 is 0. I am not able to think of anything else. So I'm sitting there scratching my head saying, that's it. So I conclude, yes, this is closed under multiplication. Now you always have to specify that it's under a certain operation. So let's look at another one here. Let's say, is the set 0, 1 closed under addition? Well, we start thinking of our examples again. Think again of examples using the numbers within the set. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. It's looking to be closed until we get to this. 1 plus 1 equals 2. Guess what? That 2 breaks us out of the closed. The door opens now. Okay? That's not a closed set. As before, you can get through that doorway. Okay? So, not closed. Because of that 1. Now, that one problem that shows us that it's not closed is called a counter example. Counter examples, you only need one. To open the door. To open. Okay? To just show that it's not a closed set. You only need one there. Okay? So it's not that I'm going to give you sets that are so restrictive to only be 2 numbers. We're actually in class going to talk about, well, all real numbers. These are all the numbers that you've dealt with. If you were in an 8th grade class that possibly went into imaginary numbers, those are the ones that we won't be dealing with. We're looking at real numbers that we can actually manipulate with modeling right here. Well, you can with imaginary numbers too, but without the use of computers and stuff, the real numbers. Let me just give you an example of what these are. I always like to think of those little China dolls, you know, that fit inside of each other, and you can snap them together. My grandma or aunt or sister, somebody used to have them. They come from Russia, and they can just build and build and build until you have a great big doll here, and inside of her are the next doll, the next doll, the next doll. Now, because I can't draw these dolls real well, I'm going to draw just boxes to kind of show you. Now, picture this. It is like the real numbers, trying to reach around my camera here, is in a big, big, big box. One that you'd get from UPS. It's contained all within there. Now, inside of this big box is a little box off to the side. In this little box, and there is irrational numbers. Okay? And inside of there are the decimals that go on and on forever without any kind of a pattern. Pi, and like a radical that's not a perfect square. Okay, now I'm going to add a little bit of color here just because I want to make sure that you get this. Now on this other part is another big, big box. Okay, inside this box is what we have rational. These are the rationals. Pretty predictable. They don't go on without a pattern. Some of these in this outer space, 9/2. That would be -4.5. 7.12. And that 1, 2 could repeat. It would be a pattern. 11.23. 3/4. Now inside of it also contains another box, but the rational title is covering, and these are within it, so they're subsets within this set. So the rational contains fractions, negatives, repeating patterns, but it also contains in it integers. Now, integers happen to be our negative whole numbers, which I know that doesn't quite make sense mathematically, but it is the numbers without the fraction. They're negative. It also contains whole numbers. Whole numbers include 0, and inside of it is contained natural or counting numbers. They're the ones that you learned as a baby. 1, 2, 3, 4. So whole numbers has 0 as well as 1, 2, 3, 4. Integers has 0, 1, 2, 3, 4, and -1, 2, 3, 4. And then building out, rational numbers have all of these as well as these. So this is what we're actually going to be looking at, closure and just a little bit of notation, subsets, and things in class. So the first thing that I want to just take you to is the question. Let's go to the smallest box, natural numbers. Whoops, I think I'm off my film. Natural numbers. Are they closed for addition? Would they be closed for addition? Well, you can think of now, here you have an unlimited number of items. So I always like to look at 1. It creates some havoc usually. I look at 0 if I can, but natural numbers don't contain 0. So we'll go 1 plus 2, that would be 3. 3 plus 1, that would be 4. As far as I can tell, again, I'm just thinking about it. Always be open when you come to class to asking others, did you get something different? But in my thoughts, I'm saying, yes, it's closed. Okay, I can't get outside of the box. Now, let's think of another option though. Let's say, are the natural numbers closed with subtraction? Well, with subtraction, sorry, I'm a little bit out of room. I'm going to come over here. If we go 4 minus 1, 3, yeah, it seems to be closed, but hopefully you're already saying, turn that around, 1 minus 4, ooh, that would be negative 3. I've just shot out of my box, and I'm clear out here at integers. So they're not closed. Hopefully that kind of makes sense. Now, in my class, as I've mentioned before, you do need to take notes to be able to refer back to in the final exam. I am not restricting you on what type of notes. I am just learning about visual notes myself. I have loved to doodle in the past. Pictures make more sense to me than words. So you guys will see me develop visually as well this year. So next thing on this topic though, we have just a little bit more to go as to what you need to be prepared for in class. Thinking back to our number sets, I want to know if I have a rational, let me make sure that rational number. Look back in your notes if you're thinking, what is that? Those are all of our integers and including fractional numbers. Okay, if I have a rational number and I'm going to add it. Sorry, I was just reading my notes, what I'm having you guys do tomorrow. If I am adding this, so we're looking at addition. To an irrational. Now, I will be honest, in math, we oftentimes have symbols that we use just so that we don't always have to write down the different types of numbers. Rational, you'll see me on the board, possibly use Q, and irrational, P. Now there's a reason why we don't use R and I. They stand for other things in math. So don't get down on us about why we chose what we did. P and Q. Those are used to just abbreviate the rational and the irrational. But let's get back to the question. Are they closed? Well, they can't be closed because they're two separate boxes. But which do we have the result of? Will we have always a rational number or always an irrational number? Best thing to do is to think of some simple examples. So 2 plus radical 2. You can't simplify it any further than that. 3 plus pi. That is the answer because of these irrational numbers. We can't do a whole lot more than that. I guess you could go into your run on decimal. This is, gosh, I'm going to be guessing 1.431, whatever it might be. You could add 2 to it and get 3.431, blah, 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 but it's still irrational. So I would say, from what I can think of, it's going to be irrational. Okay? It's going to be the P. Now, what if we have numbers, and we are multiplying this time. Irrational. What will that be? Well, we might sit here and think of all of these common ones. 2 times radical 2, that would be 2 radical 2, so that's irrational. But remember a minute ago I said always go back to 1. No, that would be irrational 2. And another number that's lovely to use because it's got its own characteristics is 0. 0 would cause 0. And so now we're over to a rational number. What I'm wanting you to always look for tomorrow in class, I want to have you watching for counter examples. Come to class ready to search out with your team counter examples. 0 and 1 are really good numbers to use in this situation. Tomorrow in class, I'm going to have you actually look at where you can find counter examples to situations like this to prove when sets are closed or not. So at this point, I think your notes are done. I hope that you enjoyed this. We'll talk to you later. See you in class.